Deep multi-output forecasting, learning to accurately predict blood glucose trajectories. Diabetes is a chronic condition which affects millions of people in the US and worldwide, and the numbers are growing by the year. Type 1 diabetes, a particularly dangerous subtype, is also on the rise. Complications, such as kidney damage, are caused in part by poor blood glucose control. By reducing periods of high and low blood glucose using machine learning methods, we can reduce the risk of complications and improve outcomes. While predicting future values, as shown, can be important, predicting trajectories of values, known as multi-step forecasting, can be even more meaningful. There are two main model types used for multi-step forecasting: recursive and multi-output. Recursive models chain predictions together sequentially in order to predict sequences. Multi-output models do not chain predictions together, but predict multiple values simultaneously. Both approaches have issues. A recursive approach is susceptible to error accumulation. Any errors made, as shown, are propagated to the next step, which can lead to inaccurate long-term forecasts. While a multi-output approach avoids error accumulation, it can fail to capture dependencies in the output window. We present two complementary modifications to fix these issues: sequential and polynomial multi-output models. In the sequential multi-output model, we model dependencies over the output window using a recurrent decoder. By predicting multiple steps into the future, the model learns to recover from recursive error accumulation. In our second approach, we approximate the output window using a polynomial function. Here, we show a degree 1 polynomial. This function is uniquely determined by two parameters, an intercept and a slope. Instead of predicting the signal values, our polynomial multi-output model predicts these parameters, breaking the temporal dependencies between outputs. We evaluate our methods on a large dataset of blood glucose data collected from type 1 diabetics. We found that our new approach reduced the rate of error accumulation, here shown in terms of absolute percent error. Beyond reducing error accumulation, our approach reduces overall error, both on average and during periods of rapid blood glucose fluctuations. By improving multi-step forecasting, we can better predict and prevent damaging blood glucose spikes. While we examine blood glucose, our multi-step models are applicable to any forecasting problem. To find out more, come visit our poster at KDD.